One of the things we saw that seemed to be important and related the initial situation with the final situation was the relative velocity, which we defined as v2 minus v1. And we can determine this initially and we can determine it finally. What we found was that v2 final minus v1 final, v2 final minus v1 final, and v2 initial minus v1 initial. What we found was that for an elastic collision, these two things were equal to the negatives of each other. In other words, v2 final minus v1 final was the negative of v2 initial minus v1 initial. For an inelastic collision, this quantity was smaller than that. And for a maximally inelastic collision, this quantity was actually 0. What we can do is actually define this relationship between them by putting in a parameter here called E, where E, or when E is equal to 1, we have an elastic collision. When E is equal to 0, we have a maximally inelastic. Whoops. And when E is somewhere in between E and 1, we have just an inelastic collision. Which could be just a little bit inelastic, almost elastic, or almost maximally inelastic. So E can be anywhere between 0 and 1. E is called the coefficient of restitution. Coefficient of restitution. And gives us a way of evaluating how elastic or how inelastic a collision is. And as we saw, for our first example, the elastic collision, these two things were equal and E was equal to 1. We looked at one inelastic collision where it turned out that E was 1/2, and then we looked at a maximally inelastic collision where E was equal to 0. All right, great. What I'd like to do now is start taking a look at some three-dimensional collisions. What happens when we have things that are not just interacting in a single dimension, but in 3 dimensions? Let's look at a particular simplification of a three-dimensional problem and see what we can figure out. Let's take a look at a general three-dimensional collision, but a maximally inelastic three-dimensional collision. So we are going to assume that our coefficient of restitution is what for a maximally inelastic collision? 0. So what does that mean for the two objects? We could have more than two objects, but we'll just start with 2. Or we'll just do 2. You can extend it pretty easily to more than 2. What are those going to do to have a coefficient of restitution equal to 0? What does that mean? Well, it means the velocities of both after the collision are going to be exactly the same. There is no relative motion, either toward or away from each other. So that means their final velocity will be 0. Their final velocities will be the same, which means what? They will come together and move off together as a single unit. So whatever the final velocity is, there will only be one final velocity for both objects. So we'll say just V final, and we don't have to say V1 final, V2 final, because they're all the same. Okay, let's imagine that we know what the initial masses are, M1 and M2, and we know what V1 initial is and what V2 initial is. How much more do we need to, are there any unknowns? I mean, is there anything that we cannot define or we cannot solve for? Is there anything that we would still need more information about? knowing that we have a coefficient of restitution of 0? Well, let's see. One thing that we do know is that momentum is conserved. So the total momentum initially, as a vector now, all three components, x, y, and z, must equal the final total momentum. In other words, we can break this down into components. We know P initial x total must equal P final x. Whoops, I'm looking at components, so I don't need the vector sign. And P initial y must equal P final y, and P initial z must equal P final z. Okay, well, great. So let's see if we can apply what we've already defined here and see what we can figure out. Well, what is the initial momentum? The initial momentum, the total initial momentum, will be the sum of the two initial momenta. And we've got the initial velocity, v1 initial. We've got the initial velocity, v2 initial. So what is the total momentum initially in the x direction? Well, what's the x component of the momentum here? Well, the total momentum is m1 v1 initial. The x component will be m1 v1 initial x. The x component of the initial velocity, v1 initial. And then plus m2 v2 initial x. That'll be the x component of the initial momentum for mass 2. And what must this equal? This must equal our final momentum, which will be the mass, but the masses are stuck together, so we know this is going to be m1 plus m2 times v final x. So from what we know here, if we know the masses, we can solve for the final velocity, the x component. And then what about P initial y? That will be m1 v1 initial y plus m2 v2 initial y. And that must equal m1 plus m2 v final y. And we can solve for v final y. And then you can imagine P initial z will be m1 v1 initial z plus m2 v2 initial z equals m1 plus m2 v final, whoops, not y, z. So, knowing that we have a maximally inelastic collision, actually that really helps us solve the problem very, very easily. As long as we know the complete initial conditions, we will be able to calculate what the final velocity is very, very easily. All we need to do is take the initial components in the x direction and basically then divide by the total mass, and that will give us the final x component. Final momentum, or I should say the total initial momentum in the y direction divided by the total mass gives us the final y component, and the same for z. Okay, very good. That's very straightforward. Let's stick some numbers in here for an example and give it a try. Let's imagine that we've got a mass of 4 kilograms moving to the right, or let's say along the x-axis. So we'll define our axes like this, x and y. So moving along the x-axis, 4 kilograms at 3 meters per second. And another object of 5 kilograms is moving in the y direction at 6 meters per second. Let's imagine then that these two things come together, they stick together, and move off as a single unit. In other words, what kind of a collision would this be? Maximally inelastic. Let's see if we can figure out what is the final velocity. Well, we know that the initial momentum component in the x direction is only going to be contributed by this mass. This mass only has a y component. This has only an x component. So this is going to be 4 times 3. This is 4 kilograms times 3 meters per second. In other words, 12 kilogram meters per second. And then to find the velocity, v final, we know that this must equal p final x. And then to find the velocity, we divide by the mass. So we know this must be p final x. And so v final x component will be p final x divided by the total mass, in other words, 12 kilogram meters per second divided by, what's the total mass? We've got 4 kilograms and 5 kilograms, 9 kilograms. Which leaves us with 1.33 meters per second. All right, what is P initial Y? Well, that's going to be contributed to by this mass only. This one doesn't have a Y component. So we'll have 5 times 6, 5.00 kilograms times 6 meters per second equals 30 kilogram meters per second. So what is V final Y? It's going to be 30 kilogram meters per second divided by the total mass, again 9 kilograms, which leaves us with 3.33 meters per second. All right, let's figure out what the final magnitude of the velocity is and the direction. So what do we have? We've got V final, we've got an x component of 1.33 meters per second. We have a y component of 3.33 meters per second. So our final magnitude, Vf, we can find from Pythagoras, 1.33 squared plus 3.33 squared root. So V final equals 1.33 meters per second squared plus 3.33 meters per second squared root. And what do we get? We get 3.59 meters per second. And then what's the direction? Well, we know that the tangent of theta will equal the opposite over adjacent, 3.33 meters per second divided by 1.33 meters per second. Take the inverse tan and we find that theta is equal to 68.2 degrees. Okay. It turns out that maximally inelastic collisions, as long as we know the initial conditions, are pretty easy to solve because we know that we've got the conservation of momentum. All we have to do is figure out what's the total initial momentum in the x direction, what's the total initial momentum in the y direction, what's the total initial momentum in the z direction, and then divide each of those by the total mass, and that gives us the final component of the velocity in x, final component of velocity in y, final component of velocity in z, respectively. So it's pretty straightforward as long as the problem is stated like this, as long as we know that it is maximally inelastic. Let's take a look at a more general three-dimensional interaction, an elastic collision, and see what we can figure out in that case. Let's imagine we've got the collision between two objects and they're in completely random directions. So we have two objects coming together that maybe come together like this and then bounce off like this. So we've got a full three-dimensional interaction. Motion in x, y, and z. How can we analyze something like this? Well, one thing we could do is simplify the problem. We're not going to change what's actually going on, but we can change the way we look at it. First of all, let's imagine we've got some incoming situation. Let's move ourselves into the frame of reference, not the center of mass frame in this case, but into the frame of reference of mass 2. Let's call this one mass 1, this one mass 2. If we move ourselves into the frame of reference of mass 2, now how do we do that? We basically subtract v2 initial from all the velocities. So every velocity we have, subtract the vector v2 initial. What does that mean? Well, v mass 2 is now stationary. So we've gone from some general interaction initially, and then something finally, but initially we've gone from some general motion initially to m2 is stationary, and now m1 is coming in at some random direction to strike it. Now let's define the direction of v1 after we have already moved into the frame of reference of m2, where m2 is stationary initially. Let's define our x-axis as the direction of v2 initial. So this is now our x-axis. So we're going to look at this thing now as basically m2 is stationary and m1 is moving in toward it along the x-axis. That is quite a simplification. We haven't changed the actual interaction, just the way we're looking at it. So what do we have? We've got M2 is now initially stationary, and M1 is approaching M2 along the x-axis. Let's draw that and take a look at it.